We've been talking about kinetic isotope effects, and I want to give you the basis to understand where they come from. And fundamentally, we talked about last time how it's because of a difference in mass between hydrogen versus deuterium, which, if you envision breaking a bond as simply getting out here to infinite distance, the 0 point energies for hydrogen and deuterium are different. Deuterium has a lower 0 point energy because of its increased mass, and so carbon-deuterium bonds have lower 0 point energy because of the increased mass of deuterium relative to hydrogen, meaning it's got a longer way to go to break the bond. And this is an overly simplistic view of the origin of kinetic isotope effects. In reality, in order to determine whether we'll see a kinetic isotope effect in a certain situation or not, we have to consider the types of vibrations that are going on in the starting material and how they will be affected by hydrogen versus deuterium. And then we need to consider the types of vibrations that are going to be going on in the transition state and how they might differ from starting material versus deuterium. All right, so let's suppose we're in a situation here where the transition state is relatively early. Right, the transition state's pretty close in energy to starting materials. And let's just say, as I mentioned before, the reaction coordinate is going to be one that has A moving away from hydrogen and B moving toward hydrogen. So this might be some vibration of, let's see, H and A are sort of bonded to each other in this case. This might be H and A stretching like this, but B going the other direction in the same way as H. In other words, it's not the reaction coordinate, it's vibration along some degree of freedom that's orthogonal to the reaction pathway. So we're taking sort of a slice of this pathway perpendicular to it and seeing vibration in some direction, and that vibration will have some energy difference between EH, the 0 point energy for hydrogen, carbon-hydrogen bond or whatever hydrogen bond, and the 0 point energy for the deuterium bond. Now let's look at the transition state, okay? So we'll take a similar slice, and because we've said the transition state is relatively early, that means it's going to resemble starting material. So if we take the slice here and zoom in on it, if it's very starting material-like, then likely the same kind of vibration is occurring in the transition state as is occurring in the starting material. And likely that difference in energy between hydrogen 0 point energy versus deuterium's 0 point energy is about the same. So so how do we do this? I'm going to try to move some things around to try to illustrate something. The conclusion that we're going to get here is there's not going to be much of a kinetic isotope effect. And I want to illustrate that, but I think I need to do it sort of to scale. So I'm going to try to, let's see, we're going to move this up here so that we're at the same sort of energy level as the transition state. Okay, and I'm going to get rid of those lines. This is transition state. Okay, and then I'm going to do the same thing down here. I'm going to try to put this view sort of with the well right there. Okay, so now I'm going to draw a dotted line here that reflects the energy, vibrational energy level of hydrogen in the of deuterium in the starting material, and do a similar dotted line here, which is the energy, 0-point energy for deuterium in the transition state. And we'll measure this energy difference, and this is activation energy. That's, we'll call this activation energy for deuterium. I'm not sure if it's actually delta G we're using, but we need a different symbol than just E because we're already using that. Is that all right? So we're going to do something similar now with the hydrogen energy. Take a dotted line here, and this dotted line here, and this is the activation energy for hydrogen. Now, if this energy difference here, which we'll call delta, starting material, and this energy difference over here, which we'll call delta transition state, what I want you to reason through is that if the difference for the starting material is the same as the difference for the transition state, then it has to be true excuse me, that the energy of activation for hydrogen is equal to the energy of activation for deuterium. You see that?
Yep.
Okay. So in that case, remember that we've said last time that the kinetic isotope effect that we see, there was maths, there it is. We've said that the kinetic isotope effect that we see is related to this equation where we could put this here, and then we could use, instead of these symbols, we could use activation energy symbols. If that number's 0, the kinetic isotope effect has to be close to 1. Okay? Which would mean, so what does that tell you? If the starting material is if the transition state is very starting material-like, then is this bond very broken in the transition state? And the answer is no. Okay? Same thing would be true, same thing can be true if it's a very late transition state, and if the vibrations in that late transition state are similarly separated like the vibrations in the starting material. So in general, very early or very late transition states have relatively low kinetic isotope effects. All right. Now let's illustrate a situation where you might expect to see a large kinetic isotope effect. We're going to do the same thing. I guess I can shrink this now. We're going to use the same kind of energy diagram, only we're going to have the transition state be neither early nor late, but fairly separated in energy from both starting materials and products. So forgive me while I erase some stuff, like all this stuff. All right, so same kind of situation, but here's our starting materials. Our products are going to be down here, but our transition state is going to be here. So all right, and we'll say, I guess, exactly the same thing as we said for our starting material, that we're going to have this vibrational energy well that's perpendicular to the reaction coordinate, and I'm going to try to adjust its height so that the well is right there. And then let's suppose that in the transition state, the hydrogen, the bond between HA and HB is nearly broken to the point that hydrogen is sort of in between. So sorry, I'm going to illustrate the transition state, and we'll say that in this transition state, you're in a situation where hydrogen is here, B is here, A is here. B and A are both moving away from hydrogen, and hydrogen is sort of motionless if it's sort of evenly shared between the two of them, right? Okay, well, if the hydrogen isn't even moving in this vibrational mode in the transition state, then the mass of hydrogen versus deuterium shouldn't matter, right? The only reason why the mass of hydrogen versus deuterium matters is if the vibration involves hydrogen. So if this vibration that used to involve hydrogen converts in the transition state to something that no longer does, then what we would say about that transition state energy diagram is that the energy, 0-point energy level for deuterium for that kind of vibration and the 0-point energy level for hydrogen for that kind of vibration is very small, right? So we're in a situation where delta, this energy difference between the two vibrational 0-point energies for the transition state is very small. And we can sort of see what the consequences of that are by doing what we did previously. So I'm going to extend a line here between deuterium in the starting material and deuterium in the transition state. This is going to be my activation energy for deuterium. And then I'm going to extend out a line for the hydrogen in the starting material and in the transition state, sorry. And this will be the activation energy for hydrogen. Which of those is bigger? Yeah, the deuterium activation energy is bigger, and it relates to the fact that the difference between 0-point energies in the starting material is greater than the difference between 0-point energies in the transition state, and therefore necessarily the activation energy for deuterium must be greater than the activation energy for hydrogen. And if that's true, going back to our equation, if deuterium activation energy versus hydrogen activation energy is positive, then this ratio has to be greater than 1. So therefore, and perhaps substantially greater than 1, all right? Okay, so again, you're seeing that the kinetic isotope effect will tell you something about how much the hydrogen bond in the starting material has changed in the transition state. If it hasn't changed a lot, you see no kinetic isotope effect because the vibrations are similar in the transition state. If it's changed a lot, you'll see a large kinetic isotope effect because the vibrations involving that hydrogen in the transition state are so different than in the starting material. All right, so that's the origin of the kinetic isotope effect. Any questions you want to ask? No? All right. So I have some more math here that I did last time, and I'm trying to determine whether it was useful or not. My notes say, for enrichment only. Do you feel like being enriched? Let's talk a little bit. We talked about how these are examples of bond breaking. We said changes in hybridization can cause secondary kinetic isotope effects. We said that those secondary kinetic isotope effects can either be normal, means greater than 1, or inverse, means less than 1. And we need to figure out how and why that can occur. So we'll call this we'll call this kinetic isotope effects due to changes in hybridization. All right. So, to set this up, we need to go back to our conception of a bond between some atom and hydrogen as being a spring, and the vibrations for those atoms, the spring constant, so on, the vibration frequency of those bonds being related to the following equations. We've got 0 point energies here, then we've got vibrational frequencies here, and you can see that those vibrational frequencies depend on not only the mass, which we say is changing, but also the force constant. And I think last time, after doing just a little bit of annoying math, let's see, well, we won't bother. Okay, so we said, just to put some numbers on it, force constant, carbon and hydrogen would be what, 13 divided by, oh darn, 12? Yeah, and this instead is going to be, yeah, you know, in your student evaluations at the end of the semester, you can say things like, he really ought to learn how to do math, or arithmetic rather, right? 12 plus 2 is 14, 12 times 2 is 24. Okay, but notice that the vibrational frequency and therefore the energy difference depends not only on these mass terms, but also on the force constant term, okay? And that force constant term is something that can change, especially if the bond between carbon and hydrogen changes, maybe not breaks, but changes during the reaction, as you approach the transition state. So let me give you an example of the kinds of changes in carbon-hydrogen bonds that can influence force constants. So here is an sp3 hybridized carbon, and I'm going to show just one particular vibration. So we're not going to say what this sp3 hybridized carbon's attached to. That's why I've got little dots here. Here is the carbon-hydrogen bond, and relative to the rest of the molecule, there's one vibrational node that involves swinging, sort of fishtail swinging of this hydrogen bond into the page and out of the page, which I'm going to try to represent. This is the out of the page, and this is the into the page swinging. In the IR frequency here is, for this, is about 1350 wave number, so basically in the fingerprint region. It's called an out-of-plane bend, And for sp2 hybridized carbons, this is stiffer and has a larger force constant. It's a stiffer vibration, and part of the reason it's a stiffer vibration is because of the electron-electron repulsion that happens as we distort this hydrogen towards this direction and that direction as it gets closer to the remaining bonds, okay? It's more sterically crowded. Now, let's look instead now at an sp2 hybridized carbon-hydrogen bond, similar vibrational mode, but notice that as this hydrogen swings out of the page and then back into the page, this same out-of-plane bend has a much lower frequency. Why does it have a lower frequency? It still involves the same mass terms, but the force constant here is smaller. So looser, we can call it a looser spring, a weaker spring, a smaller force constant. All right, so what's that going to do for us? And let's see. So let's imagine a reaction where we're rehybridizing at a carbon. Perhaps this is an elimination reaction. For example, if you compare this starting material with this one, when the leaving group is gone, because this is an elimination reaction, you can see that at this carbon we're rehybridizing from sp3 to sp2. So we're going from something in the starting material that has a larger force constant and suppose we do HD exchange, hydrogen deuterium sort of variations for this hydrogen versus this in the starting material to product. In reality, we would do both of them, but you're going from something that's sp3 hybridized to something that's sp2, something with a larger force constant to something with a smaller force constant. All right. You can show, based on stuff we did last time, sorry, this is mathy. We can show that our kinetic isotope effect is related to this difference in 0-point energy for the starting material, I'm sorry, for deuterium versus hydrogen, right? And you can show that that energy difference is equal to 1/2 times Planck's constant times the vibrational frequency, which we can pull out the constants that are similar in these vibrational force constants. So we can pull out of those expressions everything that we have in common. So let's see, 1/2 H times the difference in vibrational frequencies. But we could factor out of there the 1/2 pi. So now this is H over 4 pi. And we could also factor out of there the square root of our force constant, right? So we'll put that force constant there. And then, of course, here we're going to have what will be left inside is the square root of, sorry, it's D minus H, the square root of, for D, what is that, 14 over 24 minus the square root of 13 over 12, or something like that. But see, this energy gap, which we've called delta in our starting material, is related not only to this mass difference, but to the force constant, okay? So the larger the force constant, the conclusion here is stiffer spring, larger force constant leads to larger difference in energy, which we're just calling ED minus EH. Okay, so what we would conclude is that a bond that is that sp3 type carbon-hydrogen vibrations have larger force constants and therefore larger deltas between energy of activation, have larger energy differences between deuterium and hydrogen, right? And we could say similarly that sp2 carbon-hydrogen vibrations have smaller force constants, smaller energy differences between deuterium and hydrogen. 0-point energy, okay? So let's imagine a situation where in the transition state we are as I said, let's imagine a reaction like this, where we're going from a starting material that we have a carbon-hydrogen bond that's sp3 hybridized, then we go to a product that doesn't. And let's just hypothesize some things, and we're not going to worry about relative energies of starting materials versus products. There's some base, and then over here there'd be some base just to balance the equation. This is an elimination reaction. But based on what we said up above, if we draw our vibrational energy well here, deuterium is lower than hydrogen. Oops. And we said that this energy difference, delta, in our starting material should be large because the bond is sp3 and therefore has a larger force constant, okay? Let's suppose in the transition state, and I'm not intending to weigh in one way or another as to what the transition state of elimination reaction is, though actually we could just look at Dr. S. This is basically the reaction we want. So if you look at that carbon where we're doing the removal, this one there, it still looks basically sp3 hybridized still, right? That's not what we wanted. Bond angle 112, 121. So it's like maybe trying to be sp3 hybridized. But for the sake of argument, let's say that in the transition state, there's already a substantial amount of double bond character. All right, so let's just suppose it's nearly sp2 hybridized. In that case, what we would expect for the energy well at the top that corresponds to the out-of-plane bend for that carbon-hydrogen bond is the vibrational constant, the force constant is going to be smaller, and that means that the energy difference between hydrogen and deuterium is similarly going to be smaller. Okay, this energy difference, delta TS, and we're going to say delta starting material is greater than delta in the transition state, because this is mostly sp2, and then this is sp3. So you can see then, as we did before, and I'm not going to hopefully not belabor the point, the activation energy difference for hydrogen is again going to be lower than the activation energy for deuterium. So we're going to expect for a process that involves rehybridization from sp3 to sp2, where it's mostly sp2 in the transition state, we're going to expect a kinetic isotope effect, again using our math from before, if the energy difference because the energy difference in the starting material is greater than the energy difference in the transition state, then necessarily the activation energy for deuterium is greater than the activation energy for hydrogen. This number is positive, and we expect a kinetic isotope effect that's greater than 1. Now, it's not going to be as big as if the hydrogen were involved in the bond breaking. So we're not looking at 7, but we might be looking in the range between 1 and 2. So hybridization going from sp3 to sp2 is what we call a normal kinetic isotope effect. All right. Now imagine a situation where, go ahead.
Sorry, quick question.
Yeah.
So for this, since we're going from sp3 to sp2, the TS looks more like sp2. In this case, would we expect the products to be higher in energy than the reactants?
Yeah, I mean, so that's sort of what we're.
Nitpicky, but I was just
No. Like if you basically according to the Hammond postulate, if the transition state resembles products, it could be. The Hammond postulate works one direction, but not the other. So it says if the transition state and the products are close in energy, then necessarily their structures must be similar. But it doesn't necessarily follow that if the product and the transition state are structurally similar, that therefore their energies must be. Because there are lots of ways to be and I think the E2 reaction is a classic example of that. Do you remember learning that E2 is faster for tertiary alkyl halides than for primary alkyl halides? And the rationale for that was that, well, more substituted double bonds are more stable. But that doesn't make any sense because the E2 reaction's not reversible, so product stability doesn't matter. How do you rationalize that? Well, there must be double bond character in the transition state. But the transition state's not that close in energy to the product. Well, yes, but there's more things going on here than just the carbons. You've got starting material base and you've got leaving group as well, and that's going to affect things. Yeah. Okay, what else? So now real quickly, though I don't necessarily want to take the time to draw things out, but imagine a situation where your starting material is sp2. So the energy difference between deuterium and hydrogen is going to be small, except we need to actually write H for hydrogen. So yeah, this delta for starting material is going to be small. And then imagine you go in this reaction, whatever it is, and we're not even saying, to a transition state that's higher in energy, which is very sp3-like. And in that case, the force constant goes larger because the bond is more sterically encumbered and less free to move around. I'm exaggerating here, but the energy difference here for the transition state is large, such that it's greater than the energy difference for the starting material. So now let's draw our little line sort of estimating activation energies. Here is activation energy for hydrogen. And then let's do for deuterium. Ah, that's interesting. Because we have a bigger gap in the transition state than we have in the starting material, now the activation energy for hydrogen is actually greater than the activation energy for deuterium. And then if we go back for our equation for our kinetic isotope effect, if that's true, then this number is negative, which means the reaction is actually faster for deuterium, and that means this ratio should be less than 1. And that's what we call an inverse kinetic isotope effect. The reaction's slower for hydrogen than for deuterium, and that's because there's not as much of an energy gap in the starting material between hydrogen and deuterium, and then because it's sp2, and then you go to a more encumbered, more stiff force constant in the transition state, the gap gets bigger, and therefore it gets much slower for hydrogen. And again, this is an example of a secondary kinetic isotope effect. It's going to be, I mean, it has to be, by definition, between 0 and 1, right? Ratios can't go to 0. I mean, they can go to 0 at some, as limit as something goes to infinity, but for real reactions, you're not going to have ratios that are 0 or less than 1, especially since rate constants can't be negative. Reactions, I don't know, could they be negative? No, perhaps if we defined sign conventions, but as we've defined them, no, they're always positive. Okay, questions then? Yeah?
Would the same trend hold for sp2 to sp1? Where
Interesting. I don't actually know, but we could look that up real quick. Let's just look up CH out of plane vibrational frequencies, SP3, SP2, SP. IR handout. I don't know that this is going to be blah, 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 useful.
should we go with probably?
There will be a difference. Yeah. Oh, no, still not. Yeah, sorry, that is known because alkynes, I think, are distinctive in IR, but I don't know what it is, but we could look it up. What I don't know how to find is What I don't know is whether alkynes even do this same vibrational mode. Whether they're, I mean, because an alkyne, what is out of plane wagging? There is no plane. An alkyne is linear.
Okay. But that would still drop their energy more.
You,
There's no vibration. Maybe.
I don't know. That's a good thing that we ought to look up. Your text doesn't talk about it, and so that must mean that people haven't done a lot of experiments, but KIEs involving SP carbon-hydrogen bonds, and I don't actually know. Look that up, but yeah. Okay, other questions? What time are we looking at? Oh, shoot. So what I'm going to do now, since we don't have, I want to show you this example. I don't think the example's necessarily important enough for you to draw out yourself. It will be in the notes, but I just want to describe an experiment where a kinetic isotope effect was useful in distinguishing between one pathway versus another. So hopefully you'll forgive me for copying and pasting here. I just don't want to spend the time to draw everything, and it'll be in the notes that I post. So an important reaction in biology is an oxidation reaction which converts this amino acid into this amino acid by removing this carbon-hydrogen bond and delivering the hydride to oxidizing agent FAD. And look at the atoms that are changing. This carbon-hydrogen bond changes and rehybridizes from sp3 to sp2. Though there are some change, and there's also some changes over here in this conjugated system. And though they didn't do the isotope experiments on FAD, though they did transfer it to FAD, so I suppose you're going from something that didn't have a nitrogen-hydrogen bond to something that does. But there are a couple of possible mechanisms, and they both involve rapid deprotonation of the alpha proton to give you this basically enolate. And then there are a couple of possibilities for the mechanism, one of which is that the enolate attacks the nitrogen, sort of a conjugate addition kind of thing. And in that process, you expect the hybridization of that enolate to be basically sp2, right? So there could be resonance overlap with the carbonyl. But in this intermediate, it goes to sp3. Now, I'm not showing you the rest of the mechanistic steps whereby we get to this amino intermediate. But one proposal in their mechanism was that this is the slow step, the rate determining step, and that there is a hybridization change in the rate determining step. In contrast, they envisioned another pathway where you do, and this is something I don't really understand, single electron transfer as the slow step from the enolate to FAD. That would generate a radical amino acid species and then a radical FAD species, which would subsequently react, collapsing to form this, again, sp3 hybridized carbon-nitrogen bond. However, in the slow step, you know, radicals are similar to carbocations. They're electron poor, and they benefit from resonance as well. So if via the single electron transfer mechanism, you would predict hybridization doesn't change very much. Okay, so the slow step involves change from sp2 to sp3 for pathway A. Based on what we just talked about, you would expect a small inverse secondary kinetic isotope effect because the force constant is going stiffer in the transition state of the rate determining step, that's going to make the energy gap bigger. It's going to make it slower for hydrogen than for deuterium. In contrast, there's no change in hybridization here. So if you were to do a kinetic isotope experiment involving a carbon-hydrogen bond on this alpha carbon, you would expect really no kinetic isotope effect. So long story short, with enzyme studies, you often can't do the types of experiments you want to do if you use the actual substrate, because the reaction is going to go on and do stuff. So they used some substrate analogs that had could react via, at least through this far, and they could use hydrogen versus deuterium. You can sort of see how this structure resembles an enolate of a carboxylic acid. Hydrogen versus deuterium, they saw an inverse kinetic isotope effect, and that supports mechanism A, where you have the hybridization change in the rate determining step from sp2 to sp3. So, I mean, that's a lot of synthesis, that's a lot of work, but in chemistry we care what the atoms are doing, and this is how we know what mechanisms are, is because people have bothered to do these studies. All right, so that's enough on kinetic isotope effects. Next time, I guess, that's not our first time on chapter 8. We need another lecture on chapter 8. Next time we're going to talk about Hammett plots and linear free energy relationships. And this is kind of fun because this is, it takes some of your intuition from electrophilic aromatic substitution, but uses it in a different way. So today's Friday, right? Have a good weekend. See you Monday.